Y la pantalla se ve bien, ¿cierto? Okay, so far, let me draw this. Oh, wait, we have a problem. Sorry. Okay, so what we have seen so far is the theory of finite state automata and regular languages. Okay, so that was the topic of the first exam. Now we are moving to languages that are not regular, more complex languages, such as context-free languages. A typical, if you remember, a typical language that was not, that you can use the pumping lemma was this one. A and Bn, this set is not regular. And the idea is that the problem is you will have to count the number of A's to remember how many A's you have in order to produce the same number of B's. So basically, the idea is that final state automata cannot remember. They don't have memory. So now we're going to see a set of languages where you can actually remember something. Not everything, but something. Like this will be the typical context-free language. And the topic of the second exam will be exactly this one, context-free languages. So we have the notion of languages and some machines that are gonna be able to identify these kind of languages. Okay. You have already seen something like that. So the typical formalism to express context-free languages or context-free grammars are formalism that look like this. So here's a question for you. Have you ever seen something that looks like this? Anyone? Let's see, Joan. Are you there? Joan is not there. So how about Jeremias?
Yes, is that the Bacchus now thing?
Exactly.
Like we've seen it in logic for computational science, I think is the translation.
Yes, exactly. You have seen this, and I was hoping that you will tell me also that you have seen when you saw the syntax of Python. When you learned Python, where did you learn the syntax from? Juan Floyd? Juan Floyd? Can you program in Python? I cannot hear you. Okay, we are not very responsive today. How about Juan Fernando?
Yes, teacher.
Have you programmed in Python?
Yeah.
Where did you learn the syntax of Python?
Mm, well, like searching in internet in different pages and examples,
Exactly.
practicing.
In order to avoid having just given syntax by example, you can also give a formalism that says like this. An if statement is the word if followed by some Boolean expression, followed by the word then, followed by some statement, else another statement. So this is the syntax, this is the form of it. And it could be actually recursive in some cases. For example, here, for example, an arithmetic expression could be a variable or a constant, or this symbol means or an arithmetic expression followed by an operator followed by another arithmetic expression. You see? So an arithmetic expression is defined in terms of arithmetic expressions. So there's a recursion going on there. So the point is that these are grammars, and we're going to call them context-free grammars, and they are very important in computer science because compilers, all the languages that you are programming with, they have to define a way to check the syntax of the program. So what you're going to learn here is going to help you understand how these things work. Okay, so basically, you might have even seen this when you were in high school or even in primary school, when I don't remember if you say, like, when you say that I'm going to speak Spanish, que una oración se definía por sustantivo seguido por un predicado y luego hay un verbo. It's the same thing. You see, these are syntax, these are grammars. So you have seen grammars basically all your life. So now we're going to see the theory of this particular kind of grammars called context-free grammars. So let's see an example. Juan Fernando says he have learned by example, so let's try do that here. Wait. So you can say that, for example, an expression, let's say an arithmetic expression. An arithmetic expression could be either a number let's put it a number or an arithmetic expression with some operator, another arithmetic expression. In fact, I'm going to erase this R to know that A is from arithmetic expression. Now, what's a number? A number could be, let's say, 0 or 1 or 2 or 9. This is a one-digit number. And the operator could be either, let's say, plus or minus or multiplication or just leave it like that. Okay, so basically, this is what you all know that arithmetic expression might look like. So for example, 5 plus 3 will be an arithmetic expression. So Jeremias, you have a question?
Yes, can we call those definitions inductive definitions? Is that
They
correct?
Yeah, that's correct.
So like when we saw in inductive list definition that it was an empty list or a list with the concatenation. Yes.
Exactly.
Okay.
And now we're gonna say that, by the way, this is the intuition. Remember that we always start with the intuition about the formalisms, and then we actually give the exact definition. So right now we are giving a very simple example of expressions. So we're gonna say this is all these rules. Each one of these is gonna be called a rule, and the whole thing is the grammar. And the grammar will have like an initial symbol. In this case will be this one. And the idea is that this symbol is gonna reduce and reduce and reduce until producing something that has only symbols like this. So let's try to generate some expression here. So according to these rules, A can be reduced to A operator A. So I write that down. And now I can apply these rules again, but I could use this or this. So I could reduce to, and this A can also reduce to this num. So we can reduce this to num operator A. Okay. Now there is a rule for this one too, which is it can reduce to any of these. So I could say that this could reduce to, let's say, 3 operator A. The expression we want to produce, let's say that is 3 plus 5. To prove that 3 plus 5 can be generated. Okay, now we have rules for this one too. So these are the ones that are not reduced. Okay, so I'll apply the rules again, and I get 3 op. Let's say op is plus, then plus, and A. And finally, I reduce A. Now the only choice is reduce this one. There are not many possibilities. So this goes to 3 plus A, and A could be num, for example. So I reduce to num. And num from number can reduce to, let's say, 5, the 5 that I have here. So this goes to 3 plus 5. And now here, I do not have more rules that I can apply. So this is the end. So you can say that A can generate 3 plus 5, the expression 3 plus 5. Do you understand this? Any questions?
Yes, teacher, I understand.
All right. So something that we're going to see here are important concepts. In these rules, there are terminals and non-terminal symbols. The terminal ones are the ones that appear only on the right-hand side of the rules. So that means that 0, 1, 2, 3 till 9 are terminals because they do not appear on the left side. And also plus, minus, and multiplication. The other symbols are the non-terminal, and those are the starting one, which is A, num, and op. They appear on the left side of the rules. So they appear here. So you say that you reduce until you produce only terminal symbols. In this case, there are 3 symbols, 3, plus, and 5. Notice that I'm not performing this summation. I'm not saying this is 8. For me, this is just only a string with 3 symbols, 3, plus, and 5. So we're gonna say that this symbol, this grammar, generates 3 plus 5. Okay?
Teacher, you call the numbers and the operations, you call terminal symbols? How do you say
Yes,
that?
yes, there are terminals in any symbol. The symbol that I'm using here, the alphabet here, sigma contains the following symbols. Contains the terminals, the symbols of the grammar, sorry. We're gonna define this later, but non-terminals and the terminal ones. The terminal ones are the alphabet, and the alphabet are here the numbers from 0 till 9 plus the symbols star, minus, and plus. Okay, so meaning that these grammars are just going to generate strings. This is string. This is string that have 3 symbols. Okay, let's try to do another example. I'm gonna give you this grammar. Think of this grammar. Here, my terminal symbols are small a and small b. And the non-terminal ones are A and B, capital ones, right? So with this example, can you tell me a string that is generated by this grammar, starting with A? Anyone?
A B.
Exactly. How do I do that? I say I can reduce A to 8A, and then I can reduce this A here to AB. I'm applying this rule here. And in B, I reduce this to A, B. And then I cannot reduce any longer because I only have terminals. Good. Can someone tell me more or less what's the language of this grammar? What are all the strings that are generated by it? You can do it with a regular expression. Jeremias?
Like A star,
Mm-hmm.
and then B. It will always end with B.
Exactly. So that's all the strings that have 0 more A's followed by 1 B. Okay. This is a regular language too. Now let's write a grammar that produces a non-regular language. Try to write a language that does AN, BN. Juan Fernando?
Teacher, from the last example, the language was the terminal symbols were all the combinations of A and B.
No, the terminal symbols were only 2, A and B.
Okay.
The terminal symbols are what the strings are made of.
Okay.
So it is the alphabet, all right?
Yeah, it's the alphabet, not the language.
Exactly. Those are the strings that are there. So A's and B's. And the language was the set of all strings of A's and B's when you have 0 or more A's followed by one B. There is always a B at the end. Okay, now the question is, can somebody write a grammar for ANBN? Making sure that every string that is generated will have the same number of A's than B's. I mean, I could try with the other one, but that wouldn't work. Let's see, I'll try what we had before. AA. I have ANs here, and then I follow with B's. And B's are 1B, or, well, like this one, BB, or 1B only. Right? So this one, what would be the language of this one, Jeremias, of this grammar? Will it be ANBN?
I don't know if that's B, the lowercase one, will make it an odd. I don't know if maybe that's a problem.
Yeah, but what would be the language anyway?
A star. And B star, I think.
I guess because what you said is B plus.
Okay.
You need to have at least one B. Okay. If you want to write the other one, you can write it like this. Is 0 or you start with a B. So in this case will be A star, B star, right? When this is epsilon. Santiago Torres?
Yes, I have a question. Why is it instead of A plus A star? Because we have to have at least one A, right?
No, because you can move. Let's see. You can start with A, and this means that you can choose this or this. Then you can choose this side, B, and then with B, you can generate here. Let's say, for example, B, B, and then you can choose B again, but choose the empty one, and then you get in the string B. So B is generated here, and you do not have any A's there. Is that clear, Santiago?
Yes, completely clear.
Yeah, because you can choose where to go. This means that when you have it like this, it means that you reduce to this thing or to this thing. This is like an or. In fact, you're right, I should explain that better. The rules are always of this form. A followed by a sequence of things here. But if you write this, something like this, like, or E prime, what you really want to say is that you have a rule that says this and another rule that says this. That means this is only an abbreviation for this. It's like the way to write two rules in one. Okay.
Teacher, those are epsilons or?
Epsilons, yeah.
Those were, okay.
No, sorry, the big ones was E, the expression. But these ones are epsilons.
Oh, okay, okay.
Okay, so going back to our original question, what will be the grammar for A and BN? You just want to make sure that whenever you produce an A, you need to produce a B. How do you do that?
Maybe adding capital B after the first capital A, like A, capital A, then capital B. Like,
Let's try. Let's try. So you suggest that A goes to what?
Small a, lower a, then capital A and capital B.
Right. And then what else? Nothing else here?
B.
Or B.
Yes.
And then B is what?
Lower B.
Mm-hmm.
Then B. Or B, small, lower B.
Okay. Here you have a problem because, again, like similar to the question that Camilo, I think, asked before, you can choose to go from directly to B's, and then you can produce the string B, 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 for example. And B, B, B is not of the form A, N, B, N. You understand how, Jeremias?
Yes, I didn't see that. That's
Yeah.
a problem.
Like that. But this idea here is interesting. You might want to reconsider that idea. At least you are guaranteeing that whenever you have small a, you will have a capital B. It's not exactly what you need, but it goes on the right direction.
Teacher, the first A, the A on the lower A is needed from. O sea, es
Yes.
obligatorio escribir esa A minúscula.
Well, I don't know exactly what you mean by that. I mean, I just wrote down what Jeremias told me, but in general, you don't need to put an A here. What you are asking for the solution of the exercise, maybe.
Okay.
Teacher, can we have something like another letter like C, and that has like A, big A, B, big B?
You're breaking up. I cannot hear you very well.
No?
So try again because there was a problem with the. I'm gonna try to write what you tell me. So A goes to where, Joan?
No, not A. Uh, First, like another letter.
Another letter. Oh, that's
Yeah,
interesting.
like a Z or something like that. Yeah, that would be uh, A, and then
B,
B. Yeah,
and then
and now we define A as uh, A A big A, or empty, and a B like B B or empty.
okay, that's interesting. But this is more A star, B star again, because here an example of this is, let's try. C goes to AB, good, and then A goes to, I pick this one here. By the way, you can pick in any order. I could have, and I'm gonna do it here. I could choose B here, and then I can go to A, B, B, and I choose this B again to reduce that B, and I do it to, let's say, A, B, 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 and I choose the same B again, and I go to epsilon, so I go A, B, B. Now I reduce this A, but I can choose whatever number of A's I want. So I just choose A, B, B. And now I'm gonna choose this A to go to epsilon. So I end up with A, B, B. And this one is not of the form A and BM, has two more B's. Two B's, sorry, and only one A. So the problem here is that you have, I mean, they are independent. The number of A's you are generating here is independent of the number of B's. You gotta find a way to make sure that that doesn't happen, that they are not separated, that they are separated like that. Johan, did you see the problem?
Yeah, I saw it.
Okay, good. So Santiago, any ideas?
Yes, I had an idea. I'm not completely sure if it's gonna work. I was thinking about if we have A, then we have A, B, A
Small a?
lowercase, yeah, small a, lowercase, A, and then B, uppercase. And the other option could
Sorry, you
be
say small b, or are you?
no, uppercase B.
So like what I wrote is
Yes,
correct.
yes, what you
Okay.
wrote.
And now?
Then the other option should be A, lowercase a, the same thing that it's on the left side. So A lowercase, A uppercase, B uppercase,
A lowercase.
A uppercase, B uppercase, and on the B side
No,
should
but
be
wait. This is the same. You are saying that, I mean, these two options are the same. Maybe I
yes,
wrote.
yes, but
And that kind of.
the on the B side it should be just B. That was my idea. I was testing it out. I was trying to write
Okay, no,
a
but what
solution
I'm
for it.
saying is that, yeah, I understand, but here you are writing that A can go to this or to this, but these two are the same, so you are not actually giving two options.
Okay,
If,
so
if you
let's
write something
remove
like
A uppercase.
or B uppercase,
Yes.
and and then B is what?
B is just B lowercase b.
Like this?
Yes.
Here is the same problem because you can go from A directly to B and start to generate B's, and you don't care about the A's. You see?
Okay.
I mean, I'll give you an example. I think I already did, but A goes to B, B goes to B, B. You need a epsilon here, but in order to terminate.
Yes.
And B. So you are generating with this grammar B, which is not of the form A and BN because it has 0 A's and 1 B.
And if we place a lowercase next to the b from the right side.
Here?
No, on the other side. On the b. No. On the
Here?
A line.
Uh-huh.
On the first option. If we go to the
Teacher.
second option.
Okay, just let's start again. So
Yes.
A goes to what?
A goes to A lowercase. A uppercase. B.
B lower or upper?
B upper. And the other option is A lowercase and then B uppercase.
Here, the problem that you have is that you can generate one A, and then you are free to generate as many B's as you want because of because of this. You see?
Okay, yes.
You saw it already? The problem?
Yes, I just see the
Okay.
problem. I'm gonna try and restructure my solution.
Yes.
Okay, I have an idea.
Okay.
Only one like A, big A.
Okay, wait. So A goes to small a, yeah, and
Big A, B.
what?
Or I don't know how to say like majus A.
Ah, say
So I just say big A.
capital.
Capital A, okay.
Mm-hmm.
B,
Big capital or small?
small B, or
Uh-huh.
epsilon.
Excellent. Before you explain, this, Santiago, can you see more or less why this will work?
Yes, I do see why it should work.
Okay, good. John, can you explain your solution?
Yeah. So the problem with the other ones, or I mean, I had some ideas that maybe will work, but will shift positions with ARBs. So we could have something like AB AB. So I'm just trying to so I was trying to think how can I put the same amount of A's and B's and with A's on the left and B's on the right, and including epsilon because I need the option to have the empty string because n could be 0.
Mm-hmm.
So my idea was, well, let's put all the A's to the left, and now let's put capital A on the middle, so I can still put A's on the left and B's on the right, and one final B on the right.
Mm-hmm.
So, and or epsilon. So now I can put any amount of A's on the left, and for every A that I put on the left, I'm putting one on the right, and I can end it with an epsilon to finish.
Very good. So yeah, this to see an example of this, you have A, B, and you have not many choices. You have to do again A, B, B, and you start already seeing how these guys here are forming around with the exact same number of A's and B's. If you try again, you will go A, B, 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 and then you can go through to the epsilon part, and then you get, for example, A, B, B. Okay? So the idea is here that every time intuitively that you generate an A, you also generate a B. So you keep count of this thing. So that's the stereotypical regular language, A N B N. There are others that are interesting. Do you know what a palindrome is?
Yes.
Okay. Example will be, I don't know, la telelecado. Okay. Smaller examples, Ava, and so on and so forth. Uh, let's let us say that in this case, the alphabet is the whole English alphabet. But let's simplify things and let's say that my alphabet is only A's and B's. So an example of palindrome will be this. And now let's try to write a grammar for palindromes. Let's see, how do we define this? Palindrome is the set of A's. There are many ways, but one way that could work is By the way, does any of you remember the definition of a palindrome? I know that you know what it is, but how you define it? A palindrome is a word that what? And then we can try to write it down here mathematically.
That you can read it the same if it's like backwards or in order.
Excellent. So that thing that Maria Jose said, you can write it like this, where such as x is equal to the reverse of x. Now, you know what reverse of x is, right? So reverse of a1, a2, an is an, a1, sorry, an2. So the reverse of this string is simply the string written backwards, as Maria Jose said. So the set of x palindromes, x in, let's say, AB star, are all the strings in AB of A's and B's such that you can write it backwards and it's exactly the same. That is that x is equal to the reverse of x. Do you understand this definition then? Based on what Maria Jose said?
Yes, teacher.
Okay. Now let's try to write down a grammar for this. How that look like? This is the grammar for A and Bn. Let's try the grammar for palindromes. I shouldn't have used the same symbol. Let's call this set, give it a name. This is palindromes. And tell me normally it's not necessarily the case, but for the initial symbol, the start symbol, you use the letter, for some reason, S. You can write down, but let's say that S is my initial letter. So what would be the rules? But since I started the example with A's and B's, so let's keep it with A's and B's.
We should remain with the same amount of A's and B's, so we could use the same the prior example, where we had.
Yeah, but let's say that B BAB is palindrome, but it's not of the form A and Bn. So we have to change that. This one is a palindrome, right? But it
I have
has.
an idea.
Joan?
Yeah. Can a single A or a single B or A capital A or B capital A B or epsilon.
Very good. So can you explain it?
So first I tried to think about like base cases. So we have to include epsilon. We have to include a single A and a single B because the palindromes can be either odd or even. So by adding a single A and B, we can do that. Now we have to ensure that whatever I put on the left is equal to whatever I put on the right. So if I put an A, I have to put the same A on the other end. Or if I put a B, I have to do the same and put it on the other end. Now we just work with that and put things in the middle.
Exactly. And how do I generate this one, for example? Then is A goes to
That goes to B capital A B and then to BAB.
In 2 steps. Well done. So now we saw 2 examples of grammars. That means that now you have the intuition. Now let's try another example yourself. We're gonna take this grammar for numbers, but now I want, when you write expressions, you write like this. From the semantic point of view, you don't know you are saying 3 plus 5 times 6, or you are saying 3 plus 5 multiplied by 6. This is ambiguous, and you can define, let's say, a priority of operators. Or so you say that, for example, you give priority to the multiplications. The binding power of the multiplication is higher than the binding power of the plus. But the other simple solution is to use parentheses. So in this case, you write parentheses to really say that this is 3 plus 5 multiplied by 6. So simple exercise is, how do you add parentheses to that? I want mathematical expressions like before, but with parentheses. So what rules would you add here? And of course, these parentheses, they need to be balanced. For example, you don't want to write 5 plus 3. There is an open parenthesis here, so you need to close it. Or you don't want to write this, for example. There is an open parenthesis here, and you don't want to write 2 parentheses. The parentheses will not be balanced. So you really make sure that your parentheses are balanced. So how would you change this? Any ideas?
Teacher, you can add a rule, another rule that is named, I don't know, parentheses, and it has that inside the 2 parentheses, it's going to have a number, a num, an operation, an OP, and a num. And that's it, I think. So
Yeah, so that's the idea. So let's, I shouldn't have done this. I do it another way. You take this, but you just add another rule. And another rule is that A could be itself A between parentheses. Okay?
yeah.
Now if you can have one without parentheses, but now you can have also one with parentheses. So this way you make sure that if you open a parenthesis, you need to close it. Because each time that you generate a left parenthesis, you are also generating a right parenthesis. You see that?
Yeah.
Do you understand this example? Okay, so if you understand this example enough for examples, here is a better question. Joan actually did, he did find A and Bn, and he said that it could be this A, was it A, B, for epsilon, right? That was the grammar. So I want you to think about where it's possible to find a grammar for AN, BN, CN, which is like before, but you also have to have the same number of C's than B's and N. So, homework. Is there a grammar, context-free grammar, for AN, BN, CN. So I want you to think about this one as homework. And do you have any other questions? Maria?
No?
Any questions?
No, everything clear.
All right, so you have this homework, and this is just the intuition of context-free grammars. In the next class, we're gonna define formally what these things are, okay? So you don't have any other questions, I leave you with the monitor. Si no, que tengan una buena semana. También fin de semana, que estén muy bien, muchachos. ¿Ya terminaron todos los parciales? ¿Del primero?
Casi, profe.
Casi, profe.
Sí, profe.
Ah, bueno, espero que les haya ido muy bien. Que estén muy bien, muchachos.
Muchas
Igualmente,
gracias, profe.
muchas
Gracias.
gracias.
Profe,
Profe,
que
hasta
estés bien.
luego.
Bien.
Profe, que estés bien.
Hasta luego, profe.
Tan troll ese Frank.